examples that I simulated really quickly. So the residuals are useful for estimating residual variation, right? So the residual variation is, remember in our model right here, our residual variation was that guy sigma squared, right? That's the variance of the y's and also the variances of the epsilons. So the ML estimate works out to be this guy, the average squared residual. But most people for regression use that guy, which is not the average, but n minus 2. So you could either think of this as, well, what's the difference between n minus 2 and n between friends? You know, the ratio for a large n, n over n minus 2 is really small, so, you know, forget about it. But if you're a stickler for the details, you might want to wonder exactly why is it we don't use the MLE. And it turns out that the MLE is biased in this case, in that if you want your estimate to be unbiased, its expected value to actually equal sigma squared, then you need to subtract off 2 there, 1 degree of freedom for the intercept and 1 degree of freedom for the slope. And because we had to estimate those 2 parameters, they get subtracted out is the way to think of it. So that's why people do that for purposes of unbiasedness. But again, if you don't want to concern yourself with that level of detail, it's no different than dividing by the n minus 1 when you take the ordinary standard deviation in that you know that's just what people do. But the technical reason is for unbiasedness. So let's get our variance estimate from our data. Okay, so we have, there's repeating statements we've already done. Here we are fitting our model. But remember, we actually showed you how to fit the model without doing LM. Obviously, you're going to do LM when you do it in practice, but now you also know how to do it without doing LM. If you want to, the function summary really gives you a lot of information about the fitted model. So summary is great, but summary creates a list, and the specific element of the list, sigma, is the residual variation. It expressed as a standard deviation, and in this case that works out to be 31.84. So what we could do, just to show you that it's the same, is we could get the residuals and square them, and then divide the sum by n minus 2, and that will give us sigma hat squared, and we want to look at sigma, so we can do square root of that to look at sigma. You see it works out to be the same number. So it's interesting that you can kind of summarize variation in a kind of clever way. So let's look here, you know, n minus 1 times the sample standard deviation is this guy right here. So that kind of would represent just sort of total variation in the y's. Variation in the y's disregarding everything except maybe its mean. Okay? And then, so let's look at that and then add and subtract y hat. And then if we expand out the square and distribute the sum along our expanded square, we get that guy. But then let's take this this term right here, yi minus y hat, and this term right here, and just look at them really quickly. First of all, notice that yi minus y hat, let's add and subtract, let's see, not add and subtract anything. Let's just remind ourselves that y hat is beta naught hat plus beta 1 hat xi, and so that's what we're plugging in right here. But also remember the definition of beta naught hat is that right there. Okay, so I'm gonna get rid of some of those annotations so we can see, and then just get so collect all these terms, and you wind up with that right there. It works out to be yi minus y bar minus beta 1 hat xi minus x bar. So, which is nifty little simplification. And then doing the same sort of thing for yi minus y bar, you wind up with that works out to be beta 1 hat xi minus x bar. So take this guy and then plug these two things in with our simplifications, and you wind up with this expression right here, which you can then distribute the sum across and get that guy minus that guy right there. And of course you can churn through the details, but then you wind up with the sum of the x deviations plus the sum of the x deviation. I'm sorry, the sum beta 1 squared times the sum of the x deviations minus beta 1 squared times the sum of the x deviations squared. And of course these are both the same thing, so they equal 0. So, and I have used, throughout, if I've used it, the sum of xi minus x bar just is 0, and sum of yi minus y bar is 0. So if you're having trouble recreating these details, make sure you remember those facts. Okay, so the end result, our total variation is equal to our residual variation plus this model variation. So that's expressed as total variation is residual variation plus regression variation. And just to remind us where this equation is coming from, remember we showed that part goes to 0. That part goes to 0, and so we have those two guys right there. Just okay. And so what we could do is we could take this guy as the denominator and put it down there, and put this guy as the numerator. And because this guy is a bunch of squared terms that has to be added to another bunch of squared terms to total up to that guy, we know that this has to be less than that one. So we can describe this number as the percent of the total variation explained by this, the model variation, not the residual variation. Or it's equivalently, we could describe it as 1 minus the percent of the total variation that's left over, right? This guy right here would be the percent of the total variation that's just expressed in the residual variation, okay? And so anyway, the percent of the variation, total variation that's explained by the model is described as r squared. Oh, there you go. So-called r squared. So very briefly, I want to talk about what's the relationship between r squared and r, which is the empirical correlation between the x's and the y's. Recall that yi minus y bar, yi hat minus y bar from 2 slides ago is equal to this guy. So if we were to plug that into here, right, you can reduce that expression to this right here, which is exactly the correlation squared, where to see that, it's not immediately obvious when you look at that why that's the case, but remember you have to plug beta 1 hat, which was the correlation times the ratio of the standard deviations, plug that back into there and you'll see that's the case. So the long and short of it is, if we define r as the correlation between x and y and r squared as the percentage of the total variation explained by the model, r squared is literally r squared. Okay, and that's maybe where it gets its name. Okay, so just briefly some facts about r squared. It's the percentage of variation explained by the regression model. I'm missing an m there. I'll fix that in the repository. R squared has to be between 0 and 1. We've shown that. R squared is the sample correlation squared. We've shown that. R squared is a misleading summary of model fit. For example, you can just delete data and inflate R squared. If you have a bunch of data and you chop out all the middle data points, then that can give you an inflated R squared. And then for later, if we add terms to our regression model, it automatically increases R squared, whether or not those examples are those data points or those variables are actually useful to include. Just add random noise to a model as variables, and it increases R squared. And then here's an example. Anscombe came up with a great collection of data sets to illustrate some issues with R squared. And so they basically had, in the data set, they have basically the same mean for the X and Y's, about the same correlation for each data set. And the slope estimate is about the same, but when you actually plot the data, here's data, you can just do it in R by saying data Anscombe and example Anscombe, and you see very, very different regression relationships. One is and these all have the same R squared. This one has kind of like what we would think of when we think of a regression relationship. This is clearly a no variance kind of quadratic that you shouldn't fit a line to. Here's one that's sort of a no variance line with a single outlier. And here's an instance where you have, all of your data is at one single X value and one data point up at a large X value. All of these wind up with the same R squared. So it shows you that even reducing simple data sets down to that single number isn't necessarily the best thing to do.